in mathematics at the University of Mons, and then he has a postdoc on optimization at the University of Waterloo to work with Stephen Bavasis for 2 years. Is it right?
Yes.
2 years, and now is an assistant professor at the University of Southampton in UK at the School of Electronic and Computer Science. So in this trip is going to bring us in the theory of optimization and how optimization can be useful to solve many machine learning and artificial intelligence problems.
Okay, that's it. Okay, so the notes are here, but I don't know why it doesn't work. So I don't know. Okay. So, and also, but it's fine because first 2 days, I'm not going to touch the notes. So basically, first just introduction, overview is the what, and then, okay, basically, usually there are 3 things, okay, what, why, how. I'm not going to talk about why. The why means why we study optimization. No, so basically, it's about what and how, okay? So what is optimization? Just minimize something or optimize something. So I'm going to talk about the following, that is, what is not considered, okay? That means what topic we don't talk about. First of all is optimization in integer. That means combinatorial optimization, integer programming, we don't talk about this integer programming, okay? So that means what? That means minimize something, and x is an integer, okay? Or natural number, okay? So we don't talk about this. And it's possible we have real number, but then we have something like x is in an integer. That means you have some function g on x, and it has to be some integer function. We also don't talk about this. So that means we don't touch anything related to integer. So one example of this is a binary program. So it means what? X is 0 or 1. So it's like on off, okay? This is off, this is on. So it's a switch. So there's something that you can describe as an on-off process, then it's a binary program. So we don't talk about this here, number 1. Number 2, we also don't talk about infinite dimension. That means we don't talk about what? That means we don't talk about PDE, and we don't talk about ODE, and then anything that have this probability, that kind of thing. So why? So example here is like minimize fx again, and then this is x, and then you subject to what? PDE on x. So example, okay, I just write something like this, okay? This is PDE constraint optimization. I'm not focusing this too much. There are many reasons. Because we are in infinite dimension, then Rees representation theorem doesn't work, and then there are lots of problems, okay? Or basically, things go crazy in infinite dimension, so no. So we most likely talk about finite dimension. That means this implies what we have. We have R. We work on R. Almost forgot. We don't care about complex number either. So no complex number. So that means we don't work on complex number. In some problem, you want to work with complex number. For example, if you work on spectrum, then it's a complex number. So you want to minimize something z is a complex number and then function on a complex number. This is on imaging or engineering. You have lots of things that are complex number, and we can actually work on this, but we don't talk about this in this module. Standard thing to do is something called Weightinger calculus. It basically is just differentiation, but you differentiate with respect to conjugate, complex conjugate, and then you can have some optimization on this, but no, we don't talk about this. And then in case, let's say you handle some problem in complex number, then you either say you consider n-dimensional complex number as a 2 n-dimensional real number. A, B is just 2 real number in complex number. So again, we don't care about complex number, okay? And because of this, okay, we don't care about integer, so we work on R, so that also means we don't care about C. And then we don't work on infinite dimension, so this means we only work on finite dimension, okay? That means it's Rn, okay? Finite dimensional inner product space, or finite dimensional normed space, metric space, or finite dimensional vector space, okay? Then what's next? We also don't consider linear program, okay? So linear program means what? We have a f, we want to minimize some f. Linear program means this f is linear. So if it's linear, then it's just inner product between the x and the vector c. And of course, we can have constraint subject to, let's say, also linear program. So you can say a d inner product x is larger than f. These are values. This is linear program. We also don't consider linear program. It's because, well, whenever we have linear program, when we take the gradient of the objective function, there's no x. You just have constant vector. So a lot of things doesn't work. So we'll consider what? Non-linear. So this is a big picture. What's the big picture? We don't care about integer. We don't care about infinite dimension. We don't care about complex number. We don't care about linear thing. So in other words, what we care. So now this is what we don't care. Now let's talk about what we care. So first of all, non-linear programming. Okay, non-linear programming. That means what? That means this thing is not constant. Okay, so if a function is non-linear, okay, it's just basic calculus. You know, it's a function like this. Then if you take a slope dx, the number will change, right? So this thing will change according to x. And then what? Well, we also consider convex problem. Okay, convex problem means what? Convex function and convex set is a very important subject. Basically, 95% we are talking about it in the whole course. So that means we will talk about what is convexity. And convexity have many ways to talk about convexity. You may know, okay, convexity is you have a function like this, and then the function is below the chord. This is called Yang-Sen's inequality. Technically speaking, this is useless because when you do optimization, this thing does not tell you a lot of things. But this defines convexity. But there are actually more than one definition of convexity. Another definition of convexity is that a function is bounded below by a tangent line. And the tangent line here have a direction called normal, and this actually is a better definition of convexity. Or you can say a function is convex if the gradient is monotone, which have some picture that looks like this. Okay, I will explain it later. Or you can say a function is convex if the AP graph is a convex set, then this relates to the convex set. We'll talk about this. Let me recap. Today is introduction. So there are a lot of things I'm not going to talk about in detail. It's like overview. So 95% will talk about convex problem. As I said, I have a lot of convex definition. Some of them require the function to be differentiable. Some of them do not require the function to be differentiable. So this means what? This will include smooth and non-smooth. So what is smooth and non-smooth? Smooth means differentiable, okay? Differentiable. Or let's use a mathematical notation, C1. Okay, a function f belongs to continuous up to derivative 1, right? And we call this means continuous. This means continuous up to first order derivative. This means continuous up to second order derivative. And classically, people call this is smooth function. That means some ex something, right? But in optimization, smooth does not mean this. Smooth means C something, okay? C something. It does not need to be this kind of thing. So, for example, x squared, we also consider this as C infinity. But in optimization, after second order derivative, it becomes 0 and we don't care. But, okay, so this is smooth. Then what about non-smooth? Non-smooth means it's not this. And a classical example is absolute value. Absolute value is not differentiable at 0. Because what's differentiation? The left limit equal to right limit, right? But for this point, the left limit does not equal to the right limit. Therefore, it's not differentiable. So, this is about the convexity. And we will talk about all this in one framework by something called subdifferential. So subdifferential written like this. This looks like partial derivative. No, we're talking about subdifferential. And subdifferential is basically a generalized version of gradient. And for some of you may know, if x is a minimizer of f, that means x belongs to arc mean f. Let's say I have this, then this is not equal, this is belong to. That means what? That means f may have more than one minimizer. If I write it as equal, that means you only have one minimizer. But now if I write this, that means minimizer is not unique. But what does it mean? It means if the function is differentiable, then gradient at this point is a 0 vector. But what if this is not differentiable? If this is not differentiable, we have the following version. We have to replace the gradient by subgradient or subdifferential. Then you will ask, what is this? We'll talk about it later. And then what about this? Now this is not equal, it's belong to. That means what? 0 vector belong to a set. So this is why these two things are in the same category. Then what's next? After nonlinear and convex, these two come together, we have a lot of things. We will have a lot of things we can talk about. Then what's next? Well, then we'll call it non-convex. Okay? Non-convex means what? Non-convex means basically this is not true. But we are not going to talk about general non-convex thing. General non-convex thing actually is a very big class. It's too big. Because what's non-convex? So if a function convex looks like this, what is non-convex? This is already non-convex, right? But we most likely will not touch this kind of thing. We will touch something that is structural non-convex. A simple example is PCA, okay? Principal Component Analysis. Here's the idea. For the optimization problem that leads to PCA, that means if you write PCA as an optimization problem, actually it's a non-convex problem. But interestingly, you always find the global minimum. But isn't non-convex problem give you local minimum? How come you get global minimum? That's what I mean, structural non-convex. So it's like this. If you have a function that looks like this, then this local minima is not as good as this global minima. What about structural non-convex? It's like, okay, you have non-convex thing, but all the local minima are equally good, then it doesn't matter which one you go. And you can have something, okay, so let's say this is the value of the function. So you can have a local minima that look like this, and then let's say suddenly you have a local minima that looks like this. So this one is very flat, this one is very sharp. So some people say, oh, this is better, this is from deep learning. Then you will want to reach this local minima instead of this local minima. Then we have some way to do that, okay? So basically the big picture is, let me recap. What we don't care. We don't care integer. We don't care about infinite dimensions. That means we forget all the PDOD thing. And then no complex number, no linear. So that's it. That means we do nonlinear. Nonlinear means the gradient change is not constant. And we talk about convexity most of the time. And we will talk about some non-convex problem, but we only talk about a finite structure. That is a structural non-convex problem. There are other non-convex problems that possibly we talk about, for example, polynomial optimization, because this is also a polynomial, right? This is like a polynomial of degree 4. Then you have this kind of structure. Then for this particular kind of problem, we can actually talk about it and see it like this. For example, simple problem like this, ax minus b. This can be a non-convex problem. Even though this looks like convex, because after you write down everything in expand it in a quadratic form, okay, let's say you have a quadratic function that looks like this, okay, if this a is not positive semi-definite, then this whole thing is non-convex. Yeah, so quadratic function not necessarily convex, because this thing can be indefinite. Then you will have this kind of saddle point problem that is, okay, very difficult to draw, but try to imagine something like this. This part is going like this, and then this part is going up. So what happened at this point is convex here, but concave here. So concave in this line, but convex in this line. Then you don't know whether or not the function will go up or go down, because one direction go up, one direction go down, so you cannot tell anything. So this is not convex. Yeah, some problem like this will happen. This is also belong to non-convex problem. And then what is the random thing? Because randomness is independent of convex and non-convex. So why we talk about this? Well, the reason is basically deep learning, and that's it. Well, for machine learning people, many of them use this. So basically, it's minimizing something, what? X under expectation of, let's say, some random variable. So random variable, I will write a Greek letter, let's say lambda, okay, under some distribution, okay. And then we have a function f, and this function is parameterized by lambda, okay. And here's a contradictory thing. I said we don't care about infinite dimension, and then you see this thing have an integral. So contradiction. Yes. So most likely when we talk about this, we are not really talking about how to solve this in the very strict sense. We are actually saying we are going to solve this using stochastic gradient method. People usually call it stochastic gradient descent. Technically it's the wrong name, because stochastic gradient method can go up, so it's not descent. So basically I'm saying here is that we will talk about something like this, but under the framework of SGM, stochastic gradient method, not stochastic gradient descent. Okay. So that means we are actually not talking about this thing. We are just approximating it by what? In terms of probability, okay? That we now say, oh, this expectation is just a big Fi, okay? So this n is very big. Then, this is what? A law of large number. Then this approximates this. So basically means we will talk about this. That's it, okay? So these are like the framework. Let me recap. What we will see mostly is convex problem and convex nonlinear problem. So these are the 99% of the time. Non-convex problem will appear, for example, NMF, PCA, low-rank matrix completion. These are non-convex problems. Or something called BM factorization. Then what about stochastic? Stochastic basically is because of the deep learning, okay, or robust optimization. So this is what we will talk about. So this is what we talk about. Then what's next? Okay, what are the math we need? Okay, so it's like everything have a starting point, right? Then we need to know something as our ground. And I would say the following thing is, I assume you know, or we don't argue why this is true. You can always argue why 1 plus 1 is 2. Okay, then people say, oh, this is Peano axiom. Then I can argue, no, Peano axiom is also not the ground truth. Something is more fundamental than Peano axiom. Then it's the Zermelo-Frankel set theory with axiom of choice. Then you will argue, oh, what the heck is this? And then it keep forever. We don't argue this. So we will just say, for the 2, we assume it's true. Okay. Then the first thing is a vector space. Okay. In fact, okay, why I'm talking about this? Because vector space come from this. There's a theorem saying that all vector space has a basis. This actually is axiom of choice. And then axiom of choice is something that not everybody accepts in math. Therefore, that means there's something we can argue. This is something like y1 plus 1 is 2, that kind of thing, but we don't care, okay? And then what? Vector space, that means we need to talk about linear map, okay? Linear map. And why we need to talk about linear map? And why we talk about vector space? Because we use vector space and linear map to describe differential. Okay, what the differential, okay, of what? In Euclidean space. Okay, I just write Rn. That is, for example, okay, x power 3 log x, this. You know year 1 calculus. You know how to do this. Then what happens if, okay, what about this? This is now matrix. This is now forbidden norm of this matrix, and then due to some reason I put a power of 3 here, and then log this. How do you do this? And of course, in this case we don't write this. We write this. But okay, first of all, what is this thing and what is this thing? What are their relationship? Then this is this part. Okay, and what about partial derivative, directional derivative? There are so many things here, and therefore we will talk about this particular detail. Why this part is okay? Why we talk about this? Because we need to do gradient descent, so we need to know how to find gradient. Then we need to know what the heck is differentiation in Euclidean space. And because we need this, so therefore we need this. That's the idea. And actually not just, we actually also need some simple topology to talk about this. So basically these are the math we need. Okay? And since we talk about differentiation, that means you also need to know calculus. That means ddx, this kind of thing, okay, for this part. Yeah. Is there anything missing? No, I think that's mostly all of them. So, and of course, okay, of course, you know step theory. I mean, okay. Then, so basically, these are the idea. Of course, if you talk about calculus, then probably limit, and then you have lots of theorem and analysis. Then, yeah, it's better to know some of them. It doesn't matter if you forget many of them. For example, I forgot many of them. So we will recall those when we need it. For example, I just give you an example of this. For example, if I have a sequence. A1, A2, A3, blah, 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 blah. I want to prove A converges to A infinity. Okay? So there are many ways you can prove this, right? But there's a way to prove it. The way to prove it is I consider sum up to n term. Okay? So what does it mean? S1 is just this one. S2 is these two add together. S3 is these three add together. Then this is true if this thing converges, right? In some situation, showing this converge is easier than showing this converge. Then we use this to prove this. One of the particular example is gradient descent. Is using this. So we have x, okay, k plus 1 is a sequence, and then is what? Is the previous one minus this is called step size, and then the gradient. Again, these are just introduction, so there are a lot of detail I skipped. For example, how do you find this number? What should you do to find this number? What's the theorem about this number? Is this number exist? How big can this number be? How small can this number be? There are a lot of detail, but not today, okay? Then if I have this, then I have a sequence, right? I have a sequence. xk plus 1, okay? Or xk. Then how do you prove this converge? It may be very difficult to prove it converge. But if I do this, then it may be easier. So if I do this, I have a sum. So for example, I consider this. What is this? This 2 is just this thing. Because of this, okay, I put it here. So xk plus 1 is this whole big thing, right? Then this whole big thing minus xk is what? It's just this, right? And then now I put a norm, then it's just norm, right? Then what? Then I put a summation here, then it's the same, I put a summation here, right? Negative sign doesn't matter in norm, so we don't care about the sign, okay? Alpha is number, okay? So now I can put the number out. Let's say alpha is larger than 0, then I can just say this, right? Then what? Then I have the following. The xk plus 1 minus xk is equal. Okay, let's say it's equal. I don't care about the direction, okay? Then I have this. Okay. Suppose you know that for doing gradient descent, gradient converges to 0. Then this thing converges to 0. This thing converges to 0. That means this thing converges to 0. By the argument that sum converge means the sequence converge, then the thing inside converge. Then gradient descent converge. That's how we prove gradient descent converge. So that means we may need some calculus analysis idea or trick or method. Yeah, that kind of thing. Yeah. So that's why we need this. So let me recap what are the things we need. We need linear algebra. So this is basically linear algebra. Okay, linear algebra. I call it LA. And then of course we may need singular value decomposition, eigenvalue, that kind of thing. But I just didn't write here. Okay. And then we need what? Calculus. And this basically is just calculus. Okay, topology is not, but it's geometry. But anyway. And then we have set. Set is set theory. Because we are going to see this kind of thing for the subdifferential, so we need set theory. I don't think I miss anything. Maybe we need probability, but we only use probability when we see stochastic thing, and 99% of the time we don't see that, so we can forget about probability. And then geometry is topology. Anything? No. Yeah. So that's basically everything. Yeah. So these are all the math you need to know. So basically, linear algebra, calculus. Not necessarily you need to know the calculus at the Euclidean space level. That means analysis for Euclidean space. But if you know, it will be good. But I will talk about it actually. And then lastly is set theory. So basically, it's this thing. So this is basically calculus, these two, and topology. So basically, let me try to recap. So what you need for the math is one, linear algebra. Okay, linear algebra. What about two? It's calculus. Okay. And then three is topology. But this topology is only in the basic level. It's like what is open, what is closed, open board, what's the bound, what's compact, that kind of thing. Yeah. So basically these three things. And then what else? There are a lot of math, right? Combinatorics, number theory, ODE, we don't need. Well, we may need some ODE when we talk about gradient descent as gradient flow, but I will talk about ODE when we reach that thing. Okay. And then probability we don't need, and that. Basically these are the math. What's next? So we need this math, then let me recap. This is what we don't care. This is what we care. This is what the math. Then now let's talk about what we will see.